Hello viewers, here is Dr. Mala Das Sharma. I welcome you to my tiny YouTube channel MALACHEMPHILIC. Today I am going to start video number 125, which is the 65th episode of Chemical Thermodynamics, and the topic is Clausius Clapeyron equation, concept, derivation and application. So let's start. Clausius Clapeyron equation. Actually, Clausius took Clapeyron equation and apply it to the liquid vapor or solid vapor equilibrium for this phase transition after making a small approximation, and then derived an equation known as Clausius Clapeyron equation. So, applying the Clapeyron equation to solid vapor or liquid vapor equilibrium, Clausius derived an equation known as Clausius Clapeyron equation. For phase equilibrium between a gas and liquid or gas and solid, molar volume of the gas is much higher than that of molar volume of liquid and solid. That we know, molar volume of the gas is much higher, unless the temperature is near the critical temperature. If the temperature is near to critical temperature, in that case, vapor and liquid density are close. Then it will not be applicable. If the temperature is not close to critical temperature, then molar volume of the gas will be much higher than molar volume of the liquid or solid. In that case, this change in the volume means change in the molar volume during this phase transition, which is equal to this volume of this molar volume of the gas minus molar volume of the liquid or solid. Here we can neglect this molar volume of the liquid or solid, so it will be approximately equal to molar volume of the gas. That will be applied to Clapeyron equation. So first we will write this Clapeyron equation. So what was Clapeyron equation? Just 1 minute. What was Clapeyron equation? In my earlier video, I have derived. Actually, this Clausius Clapeyron equation is the extension of Clapeyron equation. But in my last video, if I would have added this Clausius Clapeyron equation there, that video would have been very long video. That's why separately I am making this video for Clausius Clapeyron equation. Okay. So, what was this Clapeyron equation? That Clapeyron equation in my last video I have derived, that is dP by dt, that is equal to delta H, change in enthalpy, we will write delta HM, change in molar enthalpy, divided by T into change in, this here also we are considering everything 1 mole, so molar volume, right? Now, say I am taking this liquid and vapor equilibrium. That means this is the vaporization. This process is vaporization. So I can write here delta H vaporization also. Delta H molar vaporization, whatever it is. Now this delta Vm, which is equal to VL minus, V gas, that is volume of the vapor, V gas minus V liquid, that approximately I am taking it as V gas or Vm, molar volume of the gas. Why? Because this molar volume of the gas is much higher than molar volume of the liquid. Here I have taken liquid vapor equilibrium. You can take it for this solid vapor equilibrium also. That's why I am writing here this molar volume of liquid, right? Now, so in this equation what can I write? I can write dP by dt, dP by dt, that is equal to delta Hm, obviously it is for vaporization, and T and then this is your volume of the gas or molar volume of the gas, right? Now, if the vapor behaves ideally, if the vapor behaves ideally, then what can I write? Then we know for 1 mole PV is equal to RT. So this volume of the gas, that is equal to RT by P. So in this place I can write RT by P. So my equation, that is Clapeyron equation, will become dP by dt is equal to delta Hm divided by this T and also RT is there, RT by P, that P will go up, right? I can write like this. So this one I can write it as delta Hm, that is enthalpy, molar enthalpy of vaporization here, into P divided by RT square. I can write it. Now from here I can write it like this. This 1 by P, then dP by dt, that is equal to delta Hm by RT square. Okay, we can write these things. Now 1 by P dP, this one I can write it as, next line I am writing, this one I can write it as d ln P. So d ln P by dt, that is equal to delta Hm by RT square. Okay. Now, this is your Clausius Clapeyron equation when this solid gas equilibrium or liquid gas equilibrium is not near to this critical temperature. Okay. So this is this equation is, say this is my equation number 1. This is Clausius Clapeyron equation. What is the condition? And this is already I told you, for your solid vapor or liquid vapor equilibrium. Okay, this is solid vapor or liquid vapor equilibrium. The condition is temperature is not close to, this is the main condition, temperature is not close to critical temperature, right? Now, we'll derive the integrated form of Clausius Clapeyron equation. Okay, so what is my equation? My equation is d ln P by dt, that is equal to your delta Hm by RT square. This is my equation, right? Now I can write this way. So this is the integrated form I am going to derive it. So this one I can write d ln P, that is equal to delta Hm by R into dt by T square. Okay. Now integrating the equation, by approximating, after approximating, what is my approximation? Approximating that delta Hm, molar enthalpy of vaporization. Here it is vaporization. Here I write vapor. Molar enthalpy of vaporization remains same or unchanged, remains unchanged within the temperature range. Okay, this approximation I have taken so that delta Hm I can take outside of the integration sign. So what can I write? Now I can write d ln p integration p1 to p2, and that is equal to delta Hm by r, then integration of dt by t square, it is t1 to t2. Fine. So now integration of d ln p, that will be ln p. Now I have to put the limit. Here it is p1 to p2 is equal to delta Hm by r. Now integration of 1 by t square, that means t to the power minus 2. That means what will be the result? T to the power minus 2 plus 1. That means t to the power minus 1, and down minus 2 plus 1. That means 1 minus will come. Then 1 by t. And the limit is t1 to t2. So this one I can write. If I put the limit, then it is ln log p2 minus log p1. That means it will be ln p2 by p1. That will be is equal to minus delta Hm by r, then 1 by t2, 1 by t2 minus 1 by t1. So this is equation number 2, and this is integrated form of Clausius Clapeyron equation. So this is number 2. This is the integrated form, right? Now, if I consider that P1, pressure P1 is 1 atmosphere. So 1 atmosphere means, when you know that boiling point is the temperature where atmospheric pressure is equal to the vapor pressure. So now 1 atmosphere means this T1 will be the normal boiling point of the liquid. Okay, I'll write in the next slide. So our equation just now what we have derived, that is ln Clausius Clapeyron equation, P2 by P1 is equal to minus delta Hm by R, then 1 by T2 minus 1 by T1. So this is also Clausius Clapeyron equation. This is Clausius Clapeyron integrated form, Clapeyron equation, right? Now, if P1 is equal to 1 atmosphere, then T1 will be the boiling point of the liquid, that is normal boiling point of the liquid. Then what this equation will become? Ln P2 by 1 is equal to minus delta Hm by R into 1 by T2 minus 1 by, this is the boiling temperature, T of this boiling point. Okay. So equation will become like this. Okay. One thing here you remember, this in the approximation what we have taken, this delta Hm remains constant within this temperature range. But you remember that this delta Hm remains constant over only a short range of temperature. Okay, so Clausius Clapeyron equation is not applicable when the temperature range is large. I'll write down this one. This delta Hm remains constant over a short range of temperature. Okay, therefore this equation, or I can write Clausius Clapeyron equation cannot be applied over a large temperature range. Okay, fine. Now we'll go to the application of Clapeyron-Clausius equation or Clausius-Clapeyron equation for liquid vapor equilibrium. Achha, what is our Clausius-Clapeyron equation? Ln P2 by P1 is equal to minus delta Hm of vaporization here divided by R, then 1 by T2 minus 1 by T1. Now look at here. If you know this pressure, this vapor pressure P1 and P2 corresponds to temperature T1 and T2, then using this equation you can calculate this enthalpy of vaporization of that liquid. Okay, enthalpy of vaporization we can calculate. This is number one. Otherwise, if you know this enthalpy of vaporization and if you know the vapor pressure at a particular temperature, say T1, you know P1 for T1 temperature, then you can calculate the vapor pressure P2 at any desired temperature. That is, T2 will be at any desired temperature. You can calculate this vapor pressure of that desired temperature using this equation. Okay, so Clausius-Clapeyron equation can be used for calculating molar heat of vaporization, delta H vaporization of a liquid if we know the vapor pressure at two temperatures. Again, if the vapor pressure, if the enthalpy of vaporization, delta H vaporization is known, then vapor pressure at a desired temperature can be calculated provided vapor pressure of any other temperature is known. So this is the application of Clausius-Clapeyron equation. Hope you have understood. Thank you.